Let A be the collection of programs which do halt. Let B be the collection of programs which don't halt. How large are these collections? Are they finite, countably infinite, uncountably infinite? Well, let's start by observing that the collection of all programs is countably infinite. I could just write them out in sequence, starting with the shorter programs and then going to the longer programs, and within any given length, ordering the programs by, say, alphabetical order. In this way, there would be some program 1, program 2. Oh, I should start with program 0. Why not? Program 0, program 3, and so on under this ordering. Every program would have only finitely many predecessors, because there'd be only finitely many programs that come before it in alphabetic ordering on its own length, and only finitely many programs which are shorter than it. And every program would show up at some point. So the total number of programs is countably infinite, essentially, because programs are given by finite strings of bits, or finite strings of ASCII characters, or finite strings of characters in some particular finite alphabet, and that comprises a countably infinite collection. But how about the subcollections of specifically programs which do halt and specifically programs which don't halt? Well, looking specifically at the programs which do halt just means I'm going to go through this list and strike out some of its elements. But what's left is still going to be a countable sequence. It's going to be infinite because there's infinitely many programs which halt. But it's going to be countable because it was a subsequence of a countable sequence. I'll just be left with now program 0 is the first, program 2 is the second, program 4 in what I've written is the third. It doesn't have to be this particular skipping pattern, but I'll be left with some countably infinite subsequence. Any subcollection of a countably infinite set is either finite or itself countably infinite. And in this case, both the programs which do halt and the programs which don't halt comprise infinite collections, so they aren't finite, but they are both subcollections of this countably infinite collection, so they aren't uncountable either. They're both countably infinite collections. However, even though they're both countably infinite collections, there is one sharp difference between them, which is in the question of whether the particular sort of bijection, or let's say the particular sort of surjection from the natural numbers onto these collections can be implemented by a computer program or not. In some very ideal abstract mathematical sense, there is this surjection from the natural numbers onto the collection of halting programs, and there is this surjection from the natural numbers onto the collection of non-halting programs. But is this object which we define in the ideal something we can actually implement with a computer program or not? Well, the answer is yes in the case of the halting programs, and no in the case of the non-halting programs. And let's see why that is. First, let's see how we can define a computable surjection from the natural numbers onto the halting programs. One way to do it is like this. Let's imagine a large table whose rows are indexed by all the possible programs and whose columns are indexed by numbers of steps for which we could choose to run those programs. I'm going to make a very sloppy table here. And now, in each cell in this theoretical table, we want to put either does halt in this many steps or does not halt yet in this many steps. And note that if you told me a particular row in a particular column, it would be easy to compute what value should go in that cell. I would just take the program you gave to me and the number of steps you told me to run it for, and I'd run it for that many steps. And after running it for that many steps and then finishing up, I'd see if the program had either managed to make its way through to halting, to returning a value or whatever you want to take that to mean, or not in the sufficient quantity of time. So, given any row and column, I can compute whether the program does or does not halt in that much time. I'll represent does not halt yet by an X and does halt by a smiley face. So if a program does halt at some point, of course, it will halt in any further number of steps as well. But some programs never halt. They just will have X's all throughout. That's okay. Some programs halt quickly. Some programs halt slowly. And as I said, some programs never halt. So we'll get this table, where at any row and any column in this table, it's easy to compute what value should go there. But how do we use this to get a computable surjection from the natural numbers onto the programs which do halt? Well, let's imagine ourselves to go through this table in some natural number indexed manner. We've seen previously how natural numbers can index pairs of natural numbers. So let's say maybe this is cell 0, this is cell 1, this is cell 2, 3, 4, etc. And this kind of indexing is itself computable, right? We're just going along the diagonals in a very straightforward, computable manner. Just think intuitively anything you could imagine writing a program to do, and that's what computable means. Anything where the instructions are very clear to you is probably computable. All right. And let's say at any particular natural number, we're going to output a value dependent on the corresponding cell's contents. If the corresponding cell has one of these X's in it, we'll output some particular default halting program. Doesn't matter what, some hello world program of some sort. And if the corresponding cell has a smiley face in it, then we'll output the program corresponding to that row. So in the diagram as I set it up, our output on 0 would be hello world, our output on 1 would be hello world, our output on 2 would be hello world, 3, 4, 5, 6, all of them would produce outputs of hello world. But on the input 7, we'd output program 2. On the input 9, we'd output program 0, etc. And in this manner, we're only ever going to output halting programs, because either we are in an X cell and we output the halting program for hello world, or we're in a smiley face cell, which means that particular row corresponds to a halting program, and we will output that particular halting program. And furthermore, every particular halting program will get output at some point, because every particular halting program, basically by definition, amounts to a row with a smiley face in it at some point. And that smiley face will get hit by our traversal of this table at some particular natural number index, and therefore that program will get output. And this mapping is computable because everything involved in putting it together is computable. We can computably map the natural numbers onto coordinates in this fashion. It's very straightforward sort of indexing. And we can computably determine of any pair of row and column coordinates whether that cell should be an X or a smiley face, as noted before. So we can just sit down and, with some tedium, depending on the programming language, it'll be easier or harder, but we can definitely do it, write a program that carries out this behavior. So there is, in fact, a computable surjection from the natural numbers to those particular programs which halt. However, there cannot be a computable surjection from the natural numbers to those particular programs which do not halt. And why is that? Well, suppose there was. Then we would have computable surjections from the natural numbers both onto the halting programs and onto the non-halting programs. And we could just run both of these surjections in tandem. We could start computing enumerations of both the halting and the non-halting programs, just by running these surjections on each possible input. And every program would eventually show up. This is not a very illustrative list since it's all dots, but every program would eventually show up in one of these lists, but not the other, right? Because one list will contain all the halting programs, the other list will contain all the non-halting programs, and every program is one or the other. So what? Well, by carrying out this process and eventually waiting for any particular program of interest to pop up, we can decide of any particular program of interest whether it's halting or non-halting. So as long as we have these computable surjections onto both the halting and the non-halting programs from the natural numbers, we have a mechanism of determining of any particular program whether it halts or not. Just keep computing at all the possible natural numbers from both of these surjections until the program of interest pops up, and then you know whether it's a halting program or a non-halting program. But as you've seen before, there is no computable way to determine of a program whether it's halting or non-halting in general. The halting programs you can always eventually determine to be halting, but the non-halting programs are a trickier matter. Because there's no computable manner of, in all cases, deciding either yes or no, this particular program does or does not halt, because there's no algorithm which carries that out, but we have seen how to construct such an algorithm given a computable surjection from the natural numbers to both the halting and the non-halting collections of programs, there cannot in fact be a computable surjection from the natural numbers to both the halting programs and another surjection to the non-halting programs. But we've seen that there is a surjection which is computable from the natural numbers to the halting programs. Accordingly, the only possibility left, we can conclude, is that there is no computable surjection from the natural numbers to the non-halting programs.